Okay, so imagine trying to control something really complex,
Mm.
where the rule book is kind of missing.
Yeah, or it keeps changing constantly, like things you can't easily write equations for.
Exactly. Think about maybe a swarm of delivery drones trying to coordinate in a busy city.
Or a smart grid managing all these different renewable energy sources coming online and offline.
Right. Or maybe a robot learning to put together fiddly parts it's never encountered.
For decades, we've had really sophisticated control systems, but they almost always rely on having a precise mathematical model of exactly how the system behaves.
And that seems to be the catch. When things get really complex or, nonlinear, unpredictable.
Building that perfect model, it
Yeah.
gets incredibly hard. Sometimes, honestly, it feels impossible. Traditional ways just start to hit a wall.
And that's where this deep dive really digs in. We're exploring this different approach. It's data-driven, model-free reinforcement learning, MFRL.
Right. The core idea is learning to control something just by, interacting with it, trial and error.
Crucially, without needing to build that explicit model first.
Exactly. We're diving into this analysis called the untapped frontier. It really maps out the potential and, yeah, also the big challenges of using MFRL in modern control.
So our mission here is to kind of unpack that source for you. Pull out the main ideas, the algorithms they're using, the hurdles that are still there.
And show where it's actually working in the real world already.
Think of this as your essential guide to getting up to speed on this cutting edge area.
Okay, let's get into it.
So to really get why MFRL is exciting, we kind of need to see the landscape first. On one side, there's the world we know well, modern control systems.
Yeah, modern control. It's all built on mathematical rigor. It grew out of classical control once we had the computing power, really.
Letting engineers tackle much more complex problems, right? And aim for higher goals.
Definitely. Not just simple regulation, but things like guaranteeing stability, rejecting disturbances, making sure performance is robust.
Tracking really complex paths.
And a big step was moving from, simple SISO systems, single input, single output.
Like one knob controlling one temperature.
Right. To MIMO, multiple input, multiple output. Think complex robot arms, aircraft. Many inputs affecting many outputs all at once.
And the math behind this, often it's this state space representation. Those equations like x dot equals x plus boo.
Exactly. The key idea there is the state vector x. It's basically a snapshot.
Everything you need to know about the system right now to predict the future.
Pretty much. The minimal set of variables. Like, for something moving, you need position and velocity. That's your state.
And those letters, A, B, C, D, they're like the system's rules.
They are. They're matrices, usually constants derived from physics or detailed measurements, describing how the system evolves on its own. A, how controls affect it. B, what you can actually measure. C, and any direct feed-through. D.
And because you have this model, the A, B, C, D, you can use really powerful design tools, like optimal control.
Right. Calculate the mathematically perfect control signal to, say, hit a target using minimal energy.
But, and this is the crucial bit, it all hinges on having that accurate model in the first place.
Absolutely fundamental. Built from first principles, physics. If the model's wrong, the control might be too.
Okay, now let's pivot. The other side. Model-free RL. This just flips the whole approach, right? It's all about learning from data.
Completely. Think of, like, how a baby learns to walk. Try something, fall down, negative reward.
Try something else, wobble a bit, maybe a small positive reward.
Exactly. Until eventually, step, success, big reward. It's pure trial and error, guided by feedback, like the old psychological law of effect.
And the model-free part is key here. It's different from model-based control, obviously, but also from model-based RL.
Totally different. The MFRL agent sees the system, the environment, as a complete black box. It has no internal equations for how it works.
It doesn't know the physics or the probability of what state comes next if it takes an action.
Nope. All it gets is experience. Bundles of, I was in this state, I took this action, I got this reward, and I ended up in this next state. That's it. S-A-R-S-E.
And it learns its strategy, its policy, just by crunching lots and lots of those experiences.
Right. And this usually happens in the framework of a Markov decision process, an MVP. You've got the agent, the learner.
Key environment, the thing it's trying to control.
States what the agent observes, actions what it can do. A reward function that tells it how well it's doing towards the goal.
And the policy, that's the agent's brain, its strategy.
Yeah, mapping states to actions. And the whole game is finding the policy that gets the most cumulative reward over time.
And there are different families of these algorithms.
Broadly, yeah. Value-based, learning the goodness of states or actions.
Yeah.
Policy-based, learning the policy directly. And actor-critic, which kind of combines both.
Okay, so modern control, analytical, needs a model, aims for guarantees before you run it.
White box. Knowledge first, a priori.
And MFRL, empirical, data-driven, no model needed, learns as it goes, no guarantees up front.
Black box. Adaptive, learning first.
That's a pretty fundamental difference in philosophy, a real chasm.
It really is. Modern control relies on that a priori knowledge to design for safety and stability before deployment.
MFRL's power is tackling systems where you can't get that knowledge, where the model is intractable.
But the price you pay, potentially, is unpredictability during learning. Safety isn't guaranteed. You have to test it empirically.
So the goal isn't really for MFRL to just take over, is it?
No, I don't think so. The source suggests the real potential is in bridging that gap, using MFRL for the really hard, unmodeled parts, but somehow weaving in the safety and rigor that control engineering demands.
That makes sense. And this comes out when you compare MFRL to other related things, like model-based RL.
Right, MBRL.
Okay.
It's different because it does try to learn a model first from the data. Then it uses that learned model to plan or figure out the policy.
And the big trade-off there is what? Data? Sample efficiency.
Exactly. Sample efficiency. MBRL can be way, way more efficient with real-world interactions. Once it thinks it has a decent model, it can just simulate millions of steps internally super fast.
Whereas MFRL often needs millions or even billions of actual interactions with the real environment, which can be slow, expensive, or even dangerous.
But MFRL might achieve higher final performance, given enough data, because it avoids model bias.
So if the model MBRL learns isn't perfect,
And learned models are almost never perfect.
then the policy based on that flawed model is also limited.
Right. MSRL learns directly from reality, so its performance isn't capped by how good its imagined model is.
Okay, what about comparing it to something like model predictive control, MPC? That's used a lot in industry.
APC, yeah, it's model-based, used online. At every single time step, it uses its model to predict the future for a short window,
Solves an optimization problem to find the best actions over that window.
but only actually applies the first action. Then it replans at the next step. That's the receding horizon part.
And MPC's real strength, its superpower, is handling constraints, right? Safety limits, physical limits.
Absolutely.
Yeah.
You can bake hard constraints directly into that optimization problem. Don't exceed this torque. Stay in this zone. MPC is great at that.
Yeah.
MFRL generally really struggles with hard constraints. It learns more about maximizing reward.
And the computation? MPC sounds heavy.
It's heavy online. It has to solve that optimization, sometimes a complex one, at every step. Fast. MFRL training is heavy offline, can take ages. But once it's trained, writing the policy is usually light and fast.
Yeah.
Just pass the state through a neural net.
Okay, one more comparison.
Yeah.
The classic linear quadratic regulator, LQR.
LQR is like the gold standard for optimal control. If your system is perfectly known, linear, and your cost is quadratic. Simple cases, relatively speaking.
It gives you a guaranteed optimal controller.
Yep, a simple linear feedback law. U neutralize Natch KX. Beautiful, but limited. MFRL is for the general nonlinear mess. But even for problems where LQR could work, theory shows something interesting. There's a formal sample complexity gap. Model-based methods, like estimating the A and B matrices first, then solving for the LQR controller, are proven to need fewer samples to get close to the optimal solution than model-free methods trying to learn it directly.
So theory backs up the intuition about sample efficiency.
It does. It really drives home this no free lunch idea in control.
No single method wins everywhere.
Absolutely not.
Yeah.
It's always about the trade-offs. Do you have a model? Can you get one? How much does real-world data cost? Computation limits. Need guarantees. Constraints. MFRL is a specialized tool, really powerful for that niche of model intractable problems.
If you can afford the data cost.
Exactly. If collecting tons of data is easier or cheaper than building that perfect model.
Okay, so we see the niche for MFRL. What about the actual algorithms, the tools people use?
Right. The algorithms have evolved quite a bit, specifically trying to meet control needs. Handling, high-dimensional sensor inputs like images, controlling things with continuous actions like motor speeds.
And doing it stably and efficiently.
Yeah. Let's start with value-based methods. The classic is Q learning.
Learning the quality, the Q value of taking an action in a state.
Right. And you'd store these Q values in a big table. But that only works for tiny, discrete problems. The breakthrough was deep Q networks, DQN.
using a deep neural network instead of a table.
Exactly. Suddenly you could handle massive state spaces like raw pixels from a game screen.
And DQN had those key tricks for stability, right? Experience replay.
Storing past, SAR says, tuples and above and sampling randomly for training, breaks correlations, stabilizes learning.
In target networks.
Using a separate, slower updating copy of the network to calculate the target Q values, again, stabilizes the learning target.
But DQN was still mostly for discrete actions, like left, right, up, down.
Primarily, yeah. Most real control problems need continuous outputs, voltages, torques, flow rates.
Okay, so that leads to policy gradient methods.
Right. These aim to directly optimize the policy network itself, the thing that outputs actions. Basic versions were often quite unstable, though.
But newer ones are better, like PPO.
Proximal policy optimization, PPO. Yeah, it's really a state-of-the-art method now. Very popular, especially in robotics.
What makes it stable?
It uses this clever, clipped surrogate objective. Basically, it mathematically prevents the policy from changing too drastically in one update step.
Right.
It keeps the updates within a kind of trust region.
Which helps avoid catastrophic drops in performance during training.
Exactly. PPO is known for being robust. Pretty simple to implement compared to some others, and it works well for both discrete and continuous action spaces. It's become a real workhorse.
Then there are actor-critic methods, combining value and policy learning.
Yeah, they try to get the best of both worlds. DDPG was a big step here for continuous control.
Deep deterministic policy gradient, what did it do?
It essentially took the stability ideas from DQN experience replay, target networks, and adapted them for continuous actions. It has two networks.
The actor and the critic.
Right. The actor is the policy network. It takes a state and outputs a specific deterministic continuous action.
Like output 3.7 volts, not a probability.
Exactly. And the critic is a Q network that learns to estimate the value, the Q value, of the action the actor proposed in that state.
So the critic judges the actor.
Precisely. The critic learns from the replay buffer using Bellman updates, like DQN. The actor then learns by adjusting its parameters to produce actions that the critic says will lead to higher Q values.
And it also uses target networks.
Yes, for both actor and critic, updated slowly using polyac averaging, just nudging the target network weights towards the current network weights over time. Very smooth.
And how does it explore if the actor is deterministic?
Usually by just adding some noise like Gaussian noise directly to the actor's output action during training.
DDPG was pretty influential for continuous control tasks, yeah.
Definitely. Things like robotic balancing, vehicle control. It was a go-to for a while.
And now perhaps the current frontrunner is SAC, soft actor critic.
SAC is arguably the state-of-the-art for many complex continuous control benchmarks right now. It's also off-policy actor critic, like DDPG.
But what's its special sauce?
Maximum entropy RL, that's the defining feature. SAC optimizes a different objective. It wants to maximize not just the expected reward, but also the entropy of its own policy.
Entropy, like randomness. It wants to be a bit random.
In a principled way, yes. It learns a stochastic policy, outputting a probability distribution over actions. Maximizing entropy encourages the policy to be as random as possible while still solving the task.
Why is that good? Better exploration.
That's a huge benefit. It explores more effectively, almost intrinsically. It also tends to lead to more robust policies, softer policies that don't commit too hard to one specific action if others are nearly as good. It can handle situations where multiple actions are viable.
Architecture-wise, it's similar. Actor or critic.
Yep. Actor network for the stochastic policy, usually two critic Q networks, help stabilize things further. Target networks, replay buffer. It also has this parameter, alpha, controlling the trade-off between reward and entropy, which can often be tuned automatically.
And the results.
Generally, SAC shows superior sample efficiency, final performance, and stability compared to DDPG and even TPO on many challenging continuous control tasks. It's a leading choice.
So looking back, you see this evolution from tables to deep nets for complex inputs.
Then deterministic actors for continuous outputs.
And now focusing heavily on stability, exploration, and efficiency with things like maximum entropy or clipped objectives.
Yeah, the field seems to have really converged on these sophisticated off-policy actor-critic methods as the power tools for tough control problems.
Okay, powerful algorithms exist, but getting them to work reliably in the real world, that's where the big hurdles come in. The source calls them fundamental issues, forming a kind of trilemma.
That's a good way to put it. The first, and maybe the most widely known, is just brutal sample inefficiency.
Needing insane amounts of data.
Insane amounts. Millions, billions of interactions sometimes to learn from scratch. For a physical robot or industrial process, that's often completely prohibitive.
Takes too long, costs too much, risks breaking things.
Exactly. Hardware wears out, you waste energy, time. And it gets even worse if your observations are high-dimensional, like camera images. Learning relevant features and control from sparse rewards takes even more data.
So how do people cope? Simulation seems key.
Sim-to-real transfer is probably the most common approach. Do the bulk of the learning, the billions of steps in a fast, safe simulator. Then, hopefully, transfer the learned policy to the real hardware.
Hopefully being the operative word there.
We get to that. Another big strategy is offline reinforcement learning.
Learning from data you already have.
Right. Instead of interacting live, you learn from a huge static logbook of past experiences, maybe from human operators, old controllers, sensor logs, whatever you've got.
That sounds amazing for industries with tons of historical data.
It's very promising. Also, things like imitation learning, using expert demonstrations to give the agent a good starting point, can dramatically cut down the exploration needed, and algorithms like SAC with better exploration help too.
But sim to real, you mentioned the hopefully. That brings us to the second hurdle, the reality gap.
The big one. Policies trained purely in simulation often just fail when you put them on the real robot or system.
Because the simulator is never perfect.
Never. There are always subtle differences. Friction, the sim didn't capture perfectly, tiny delays in actuators, sensor noise, unmodeled aerodynamic effects, infinite details.
And the RL policy might have accidentally learned to exploit some weird quirk of the simulator.
Exactly. It overfits to the simulation's specific physics, even the flaws. When those flaws aren't there in reality, the policy falls apart.
So all that simulation time could be wasted. What's the fix?
A popular technique is domain randomization. During simulation training, you deliberately randomize the parameters of the simulation mass, friction, latency, motor constants, even visual textures.
So the policy has to learn to work across a whole range of conditions.
Right. It forces the policy to become robust to uncertainty, making it more likely to work in the real world, which is just another variation it hasn't seen.
Other ways.
System identification can help use some real-world data to build better models of specific tricky components to the simulator. Domain adaptation techniques try to learn a mapping between simulation data and real data. And again, imitation learning using real-world demos can bridge the gap.
Okay. Sample inefficiency. Reality gap. What's the third leg of this trilemma?
This one's critical for control. The guarantee deficit. Safety and stability.
The trial and error nature means things can go wrong during learning.
Terribly wrong, potentially.
Yeah.
Especially early on when the agent is exploring randomly. It might take actions that are unstable, damage equipment, or are simply unsafe. MFRL offers no inherent upfront guarantees about safety or stability.
And that's a deal breaker for cars, power grids, medical devices.
Absolutely unacceptable. You can't just let an RL agent randomly try things on a safety-critical system.
So how do you build safety in?
This leads to the field of safe reinforcement learning. One way is to formulate it as a constrained MDP. Add explicit safety constraints alongside the reward objective. Algorithms like CPO try to maximize reward while provably satisfying those constraints.
And this seems like the perfect place to bring back classical control ideas.
Exactly. This is where the synthesis happens. Using concepts like control barrier functions, CBFs, or Lyapunov functions from control theory.
These mathematically define a safe region of operation.
Precisely. You can then build a safety layer, or a shield around the RL policy. The RL agent suggests an action.
But the safety layer checks it first.
Checks if executing that action would violate a constraint or leave the predefined safe set. If it would, the layer overrides or modifies the action to the closest safe alternative.
So you get the learning power of RL, but with a safety net from control theory.
It's a very powerful fusion. You're combining model-free learning with model-based safety analysis. Offline learning from inherently safe datasets can also contribute.
So this trilemma, sample efficiency, safety, performance, they're all interconnected and often in tension.
Definitely. If you add a strict safety layer, like a CVF, it might restrict exploration, which could hurt sample efficiency or even prevent finding the absolute highest performing policy if that involves operating near constraint boundaries.
And trying to maximize performance might push you closer to unsafe regions.
Right. And sim-to-real helps sample efficiency but creates the reality gap, which itself can cause safety or performance issues if the sim mismatch is significant. Domain randomization helps bridge the gap but might require even more simulation data.
It sounds like there's no easy answer.
The source suggests the most promising solutions involve combining these strategies. Maybe start with offline RL on safe data, then sim-to-real fine-tuning with domain randomization, and finally deploy with a runtime safety layer. You need this control-aware RL perspective.
Okay, let's see it in practice. The case studies really show how this is being used now.
Yeah, and they really highlight these hybrid approaches and the dominance of algorithms like PPO, DDPG, and especially SAC.
Robotics seems like a big area. Manipulation, locomotion.
For sure. Quadruped locomotion, getting four-legged robots to walk.
Ew.
One study got a robot learning to walk robustly on tricky terrain in about 20 minutes of real-world time.
Wow, 20 minutes. How?
It wasn't just the algorithm, PPO or SAC variants, but really clever engineering of the whole training process, curriculum learning, careful reward shaping. Another study used just one human demo to bootstrap the learning, then used MFRL just to add robustness.
And robot arms doing tasks.
Often sim to real. Training robot assembly, using PPO with lots of domain randomization in sim, then deploying on the real hardware. Or complex stuff like balancing a ping pong ball with SAC, super hard to model perfectly.
But sometimes MFRL is just one part, like in robot soccer.
Yeah, maybe use MFRL to learn a really dynamic sub-skill, like a powerful pick, but embed that learned skill within a larger, more traditional planning and control system. Use the tool where it fits best.
What about autonomous systems? Cars.
DDPG and related algorithms have been used for things like lane following or adaptive cruise control. One cool hybrid approach mentioned was pre-training in a simulator like SciLA.
Then fine-tuning using a replay buffer filled with real human driving data.
Exactly. Leveraging existing safe driving data makes the learned policy more robust and practical much faster.
And that adaptive PID tuning example, that sounds really neat.
It is. Using PPO not to replace PID, but to online tune the PID gains for a robot arm. It showed better performance than a fixed PID or even other DRL approaches on that task, a great example of enhancing classical control.
And it's moving into bigger industrial systems too. Energy, process control.
Seems so. SAC was used for voltage control in a simulation of a large chunk of the East China power grid. Trained offline using historical SCADA data, then updated periodically online, shows potential even for critical infrastructure.
Home energy management.
Yet PPO used to optimize a complex household goal, juggling electricity bills, battery health, and EV charging anxiety, achieved significant cost savings compared to baseline rules. It's solving complex optimization under uncertainty.
Even chemical engineering.
SAC used to automate the design optimization of a distillation column, interacting with standard industry simulation software, Aspen Plus. MFRL acting as an intelligent optimization layer on top of existing tools.
So the clear themes from these examples are hybrid approaches dominate.
Absolutely. Mixing simulation, real data, classical control concepts. That seems to be the winning formula right now.
And algorithm-wise, it's mostly those off-policy actor-critic methods, PPO, DDPG, SAC.
Because they handle continuous actions well and tend to be more sample efficient in practice, which is just critical for these real-world applications.
And MFRL is usually acting as a highly skilled component, not the whole show.
Yeah, integrated intelligently, playing to its strengths, often complementing rather than replacing traditional methods entirely.
Okay, so wrapping this all up. The core finding from the analysis seems clear. MFRL is genuinely powerful, especially for systems with a modeling deficit.
Where building a good traditional model is the main roadblock. Too complex, too nonlinear, too uncertain.
But it comes with those serious challenges we discussed. Sample inefficiency, the reality gap, and the lack of built-in guarantees.
Yeah, those aren't minor details. They are fundamental hurdles.
So the path forward isn't just about tweaking algorithms, it's about tackling these head-on.
Right. Research focus needs to be on things like provably safe and efficient RL, really merging learning theory with control theory, using CBFs, Lyapunov stability, formal methods.
Building that safety layer in from the start.
Exactly. Also, generalizable offline RL. How do we learn effectively and robustly from potentially biased, incomplete static data sets? That's huge.
And improving sim to real. Better sims, smarter randomization, faster adaptation techniques.
Making that transfer more seamless and reliable. And finally, thinking about principled hybrid architectures. How do you best combine RL's strategic learning with classical control's reliable execution? Maybe hierarchical systems.
So the final verdict isn't MFRL replaces modern control, it's more nuanced.
Much more. It's a specialized, powerful tool for certain hard problems. The future isn't replacement, it's synthesis.
Hybrid systems that intelligently blend the strengths of both worlds, the rigor and safety of control with the learning and adaptability of RL.
That seems to be where the real breakthroughs will come.
So a final thought to leave people with. Think about systems out there that are currently just too complex, too unpredictable to control effectively or efficiently using traditional methods.
What kinds of intricate interactions or adaptive behaviors or massive optimizations might become possible with this next generation of hybrid learning-based control systems? What could you control that seemed impossible before?
So, we've taken this deep dive into model-free reinforcement learning for control. We've seen its potential for tackling these really tough, complex problems.
And we've also confronted the very real hurdles the data needs, the sim-to-real gap, the safety concerns.
It's pretty clear it's not about throwing out decades of control engineering. It's about adding a powerful new capability to the toolkit.
Especially, yeah, for those systems where getting that perfect model is the hardest part of the whole problem.
The future really does seem to be about combining the best of both worlds. Hopefully, this discussion gave you a good sense of this exciting frontier.
And maybe spark some ideas about what this blend of learning and control could mean in areas you're interested in.